Okay, so in the last class we'd computed the scattering amplitude for four tachyons in open string, in the closed string theory, and we got S K1, K2, K3, K4 is equal to now I'm going to write okay, first let me write what we wrote last time, which was 2 pi, okay, gamma of minus alpha of S, gamma of minus alpha of T, gamma of minus alpha of U divided by gamma of minus alpha of S minus alpha of T, gamma of minus alpha of U minus alpha of S, gamma of minus alpha of U minus alpha of T. Okay, this answer is correct up to an overall up to some overall constants, which we will come to, which will be part of the point of this class if we reach there. But before we get to these overall constants, first let's look at the which we'll of course talk about. But before we get to these overall constants, let's look at the energy dependencies. Okay, now there are two things I want to start. There are three things I want to say about the energy dependencies here. Okay, we have to remember what this alpha was. Alpha of x was equal to 1 plus alpha prime by 4 times x. Okay, so now the first thing we're going to ask ourselves is, what is the analytic structure of this S matrix? Okay, now let's see. Gamma functions have poles at negative integers or 0. Okay, so any negative whole number gives us a pole of the gamma function. Okay, so if we have a value like this, if it happens that one of these three guys is negative, okay, and there is no corresponding compensating cancelling factor, then this thing is going to have a pole. So let us first study the poles. Okay, let us first study the poles in S. Okay, now you see, since we will work at S but for arbitrary values, arbitrary complex values of T. Okay, where this guy has a pole, this guy will in general not have a pole. This guy will in general not have a pole because T is arbitrary. So if alpha of S is a negative integer, minus alpha of S is a negative integer, minus alpha of S times minus alpha of T can only be a negative integer if something very special happens. Okay, we'll come back to looking at what that very special thing might be, but for now, in general, this cancellation is not going to happen, for general T. So let's ignore that possibility.
Yeah, the only worrisome term would be alpha T plus alpha U, which is by constant, I think, would be 1 plus alpha S. But if alpha S minus alpha S is a negative integer, 1 plus alpha S is necessarily a positive integer.
Exactly.
Which has
Exactly. So in fact, why don't we just write this in terms of single variables? Okay, so as you said, let us remember that alpha plus alpha was equal to minus 1, and therefore minus alpha plus minus alpha
is 1 plus alpha U.
1 plus alpha U. Yes, exactly. So this is equal to gamma of minus alpha of S, gamma of minus alpha of T, gamma of minus alpha of U divided by gamma of 1 plus alpha of u, gamma of 1 plus alpha of t, gamma of 1 plus alpha of s. And exactly as Upmanyu said, if this is a negative integer, means alpha is a positive integer 0, and therefore all these arguments are positive integers. Okay, so there's no cancellation going to happen, exactly as you said. That was okay. So now let us look at the poles in S. The poles happen whenever minus alpha of S is equal to minus n, where n is any value. Okay. When that happens, we'll figure out what this means in a moment. But even before that, when that happens, let's compute the residues of the pole. Okay. For the residue of the pole, what we want to do is to set alpha of S to be minus n. So we have alpha of S is equal to n. But we also know that alpha of S plus alpha of t plus alpha of u was equal to minus 1. And therefore we have n plus this is equal to minus 1. And so we can write it all in terms of t, for instance. Okay, so we'll get alpha of u is equal to minus 1 minus alpha of t minus n. Okay, so now also we'll let us remember that gamma of n plus 1 is equal to n gamma of n. Okay, so now I'm going to remind ourselves the nature of the pole at alpha equals minus n. At alpha equals 0, the pole is a simple pole. Yeah. We know that. So how does it go at alpha equals minus 1? Well, gamma of 0 was exactly. Exactly. Gamma of 0 was gamma of 0 was equal to minus 1 times gamma of minus 1 using this formula. Yeah. And then gamma of minus 1 is equal to minus 2 times gamma of minus 1 and so on. So what we get is minus 1 to the power n times n factorial times x gamma of minus n plus x when x is small goes like this. Is this clear? Okay. So suppose we expand alpha of s. So what we do is to say minus alpha of s is equal to minus n plus x. When we do that, then what do we get? We get minus 1 to the power n factorial by x from here. Okay, and then here we get gamma of minus alpha of t, that's whatever it is. This is gamma of minus 1 minus n, or no, plus 1 plus n plus, I got this sign, this is all correct, right? Plus 1 plus x plus alpha of t divided by here we just replace with n minus x. So whatever, gamma of 1 plus n minus x, but x we set to 0 because it's not singular. Gamma of 1 plus n, so this will cancel this n factorial actually. Okay, then we get here gamma of 1 plus alpha of t, and here we get whatever it is, gamma of 1 plus minus 1, so minus alpha of t minus n. Okay? So as we said, this guy and this guy cancel, and this is the residue of the pole. So some particular function of t. Okay. Now, what particular function of t actually we can do better? Because notice, exactly. Notice that this quantity has, the argument of this is n more than the argument of this. And notice also that the argument of this is n more than the argument of this. And then we use the property that gamma of n plus 1 is gamma of n times gamma of n. So this residue here is what? So this is minus alpha of t minus 1, okay, minus alpha of t minus 2, all the way up to, this guy is going to cancel with this guy, minus alpha of t minus n. Okay, and then similarly, this guy here is n plus alpha of t into n minus 1 plus alpha of t up to 1 plus alpha of t. Now notice that these are actually the same, up to an overall minus 1 to the n. Is that clear? That minus 1 to the n cancels this minus 1 to the n. Okay, and so what we get in the end is a very simple residue. These gammas have gone away, and the residue is alpha of t plus 1 into alpha of t plus 2 up to alpha of t plus n. The whole thing square divided by x. Notice that this thing is a polynomial of degree 2n in t. Now, what we should have been, from the general analysis we had in the previous classes, we should have been able to predict that. Can somebody tell me why we expected a polynomial of degree 2n? For the residue of the pole? Okay, first let's remember what a pole is. When do you get poles in Feynman diagrams? You get poles in Feynman diagrams when you've got tachyon, some field, we don't know what it is. Okay? Now what is the mass of this field? The mass of this field is, well, minus alpha of s was equal to minus n, that sets the mass. So that's 1 plus alpha prime s by 4 is equal to n. So that is equal to s is equal to n minus 1, 4 by alpha prime. This should be identified with the m square of the field. Now you remember the formula for closed string for the masses of closed string states. We had 4 by alpha prime times level minus 1. So this tells us that the things that have alpha of s minus alpha of s is equal to minus n, or alpha of s is equal to n, the things that can propagate in the middle in order to produce these poles are all the states at level n. Okay? Now, do you remember last time we argued that states at level n cannot have spins larger than, the spins have to be less than or equal to 2n? Right? Because you could have the biggest spin is del x, del x, del x. Okay? We also argued that if you have spin s exchange, the function of t that comes above the pole is completely determined for spin s exchange, and in particular was a polynomial of degree s. So since s is less than or equal to 2n, the whole residue here had to be a polynomial of degree 2n plus a polynomial of degree 2n plus minus 2 and so on. But you know, all those are polynomials of degree 2n. A polynomial of lower degree added to a polynomial of degree 2n gives you a polynomial of degree 2n. So what you should expect here is a polynomial of degree 2n, and indeed you find it. Okay? Now, as an exercise, one can do the following. One can take this function here, it's a simple polynomial, and decompose it. I didn't work it out for you in detail, but it is possible to work out exactly the function of S that appears behind spin S exchange. Okay? And the function of S is some polynomial of degree 2. In fact, in t, sorry, in t, function of t. And it's a polynomial of degree S. And you know, so basically these are orthogonal polynomials very closely related to spherical harmonics. In fact, I'll tell you what those polynomials are. Suppose you take scalar spherical harmonics in 3 dimensions. There is one special spherical harmonic that preserves SO2 out of SO3. That is rotations around the z-axis. That is the m equals 0 spherical harmonic.
Yeah.
That is some function of cos theta.
Just Legendre polynomial.
Legendre polynomial cos theta. Now, just like that in every higher dimension, if we were an SOP, choose one axis. There is a unique spherical harmonic that preserves that axis. Okay? That spherical harmonic, because it's rotationally invariant, can only depend on the angle between where you are and that axis. That angle we'll call cos, so it can only depend on cos theta. So in every higher dimension, while spherical harmonics in general are complicated because they're labeled by many numbers, there's one distinguished spherical harmonic that is simple. Namely, it's a function only of cos theta. This function here is the same function of t, or maybe 1 minus t. Is that spherical harmonic as a function of 1 minus t? I won't try to give you the argument for that. Okay? But spherical harmonic in which dimension? Spherical harmonic in the dimension that is relevant for the little group analysis of massive particles. So spherical harmonics of SO d minus 1. So in 4-dimensional scattering, the spherical harmonics that appear are Legendre polynomials. Okay? But in 5-dimensional scattering, the spherical harmonics will appear as spherical harmonics for 4 dimensions. So whatever polynomial that is, they have some names. Gegenbauer, some name. Okay, but whatever, it's some simple thing, well studied, they form orthogonal polynomials. Because of the orthogonality, it's easy then to decompose this function into the various coefficients. Okay, now I won't do that for you, okay, but it's possible to do. Okay, at least for small numbers it's possible to do. I'm not sure, you know, for n equals 2, 3, 4, 5, it's easy to do. And now, from this picture, can you tell me what you should expect? So if I take the coefficients of each of these polynomials, what should I expect? Is there any expectation about these coefficients?
Integers?
No? No, it's weaker than that. It should just be positive. Okay. Why should it be positive? You see, because this thing comes with some coupling. That coupling is a real number because we're dealing with a unitary theory. Couplings in a Lagrangian are real numbers. We've taken out all the i's and so on outside. So we're working with the convention, the scattering amplitude is directly the coefficient in the action. Any i's that go between them we've taken out. Okay? But this coupling is the same coupling. So the coupling could have been any real number, but what appears? Because, yes, because this is tachyon, 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 tachyon. What appears is g squared. Okay? So every diagram here has to have a polynomial, has to have a pole for any spin S, independently for each spin S exchange, with a positive number. And you know, it's a remarkable thing about this function. Of course, it had to work because string theory is consistent. But if you didn't know that it had to work, you get a bunch of integers. And for an infinite number of these, you know, this should work for every n. All these integers have to be positive. Okay? And Now, this analysis also has to work. Now, we've done this analysis at 26 dimensions. But really, we could have done the scattering in any subset of those 26 dimensions. Chosen the gravitons to lie in that subset, and nothing would have changed. We could have put the other dimensions on a torus, and nothing would have changed. So this had to work for d less than equal to 26. When you try to check it out, it turns out that these things are positive, though it's actually very hard to prove directly. I don't think I've ever seen a direct proof of this statement. But if you just put it on a computer and find all these coefficients, you always get something positive. But you go to higher dimensions at 26. I'm not sure exactly at 27, but certainly if you go to dimension 50, and you take the same thing, expand in the Gegenbauer polynomials, that you get negative numbers. So that string theory's way of telling you that everything worked when you were in 26 dimensions, or anything you can get by compactifying 26 dimensions. When you go to high dimensions, you get negative numbers. You get non-unitary theory. Okay? Another way of saying it, okay, so let me say it again. The fact that our diagram had only poles, the first remarkable thing about this thing was that the only singularities in these amplitudes were poles. Because we're doing tree-level amplitudes, that had to be the case. But we were doing some integrals over some world sheets and so on. From that point of view, it wasn't clear. But we got only poles. The second thing about it was that the coefficients of these poles were all positive. Okay, both these statements in a way can be thought of as a manifestation of Kutkowski's rules for tree diagrams. Kutkowski's rules are the statement that the singularity in any S matrix is the square of the on-shell amplitudes. Now, poles have delta function type singularities. More precisely, Kutkowski's rules tell you that the singularity in any S matrix can be obtained by taking the propagator which you cut and replacing the propagator by a delta function. Now, what is the singularity piece? Singularity is same as imaginary part. This is different. What's different when you go from up and down? What's the singularity in a pole? It's a delta function. Because pole is principal 1 over x is principal value of 1 over x plus I times or minus I times delta function, I pi times delta function. Singularity of that pole was a delta function, and that precisely is the kind of thing that would come from Kutkowski's rules, because you replace the propagator by a delta function. And then you replace this by a delta function, but this comes wherever it is, so you get the g square. So it had to be that quantity square times a pole times a delta function. Okay, and that's working beautifully here.
I have a question.
Yes.
So, non-critical string theory can still work if, let's say, we modify our CFT content by some linear dilaton CFT.
Yes. Yes.
Like that. But if we have a non-critical string theory in which, let's say, string theory in large number of dimensions in which the scattering amplitudes themselves don't make sense, would that be a valid string theory, or can we fix this by adding something else?
No. If the scattering amplitudes don't make sense, they don't make sense. But if you want to go above 26 dimensions, the linear dilaton has to be in the time directions. Okay. Therefore, it's impossible to have a graviton whose polarizations lie outside the linear dilaton directions. So no matter what subspace of space-time you choose, you will always have to choose the linear dilaton part. So this calculation will be modified. Okay, so we'd get a new answer. Actually, even that answer is very strange, because since now in this background there's no time translational invariance, so energy is in general not conserved in this. So the whole formulation of scattering you'd have to think through again. So it's a different kind of question. Okay, it's different when it's space translation invariance is broken. That less than 26 dimension you get linear dilaton space. There you can sort of choose to ignore that direction. Take polarizations and momenta that lie in the transverse directions. Then everything is translationally invariant in the direction in which you're scattering, and then scattering amplitudes basically are unchanged. Did you understand that? Let me say it again. The formalism of string theory is like this. We have a CFT. But suppose you have the formalism such that it's CFT1 times CFT2. Direct product plus CFT2 on the world sheet. let's say that this guy was r to the power d, when d was less than 26. And this guy is anything. Now if you compute scattering amplitudes with vertex operators in this part, it's completely insensitive to what that is. Because it's the same calculation. Okay? So if your scattering amplitudes are allowed to be in the flat place part, you get the same answer as before. So linear dilatons for d less than 26. When you scatter only the gravitons without no legs or momenta in the direction of those polarizations are good, but then you just get the same answer as before. Okay? Whereas in time, unfortunately, you don't have the option of doing that. Okay? Excellent question. Okay. Can I go on 5 more minutes? Is it okay? You missed 5 minutes of that Gelman thing. Okay. There's this Gelman thing which Upanyu was requesting we break class for. There's a retrospective for Gelman. Sorendu's talking now, and Amol will, about his contribution for strong interactions. That actually, even I want to know, what did he do exactly? I only have pop science knowledge of what he did. Okay, okay. But anyway, let's keep going. Let's keep going for 5 minutes. So this is the first really important thing: the pole structure of these amplitudes. The fact that the residues are polynomials at the right degree, and that the coefficients, when you decompose them, are positive. Any questions or comments about this? Okay. Now, the second thing I wanted to tell you about was about the, so I'm rubbing this out. The second thing I wanted to tell you about was about the large S fixed T, large S, large T behavior. So, in yesterday's class, we computed what S was. S was equal to, in center of mass frame, m squared plus k squared. Whereas T was k squared into 1 minus of k squared into 1 minus cos theta. Okay, now suppose what we do is to go to k goes to infinity. So when k goes to infinity, we can basically ignore this term. So T divided by S. So then T is equal to minus alpha times S, where alpha is equal to 1 minus cos theta. So what we're going to try to do is to study what happens to the scattering amplitude when we go to large energies, that's large k, but fixed angle, that is fixed alpha, because fixed theta. Okay? So what do we have to do? We have to substitute every time we see a T, we substitute T is equal to minus alpha prime S. And because the momentum part dominates over the energy part, instead of using S plus T plus U is equal to 4m squared, it's effectively 0. So U is equal to minus minus 1 plus alpha times S. So let's write it as 1 minus alpha.
Yeah, 1 minus.
Minus of 1 minus alpha S. Okay? So let's substitute that into this formula. I shouldn't use alpha here. Let me write zeta. I should really let you go, but I'll just finish this part and then we can go. Okay, now this alpha of S was alpha prime by 4 times x. Everything's very large, we can ignore the ones. Okay, so this is gamma of minus alpha prime by 4 S, gamma of plus alpha prime by 4 S times zeta, and gamma of, this is also plus 1 minus zeta to alpha prime by 4s. Okay, let's alpha prime by 4s appears everywhere. So let's say alpha prime by 4s is equal to x. Okay, so gamma of minus x, gamma of zeta x, gamma of 1 minus zeta x divided by gamma of, now all of these, oh, now actually I've been a bit careless. I've been a bit careless. I've been too fast in dropping ones. No, but actually they will appear uniformly, so I've been okay. I'll just, right. The only approximation I made so far is in what alpha was.
Yeah.
So that's okay. But I shouldn't ignore 1 plus alpha, because gamma of 1 plus alpha is alpha times, yes. So it's not something very small. Okay. But anyway, there is, let's keep it. In the end, we'll be able to ignore it. So gamma of this is because it's the opposite direction. Many of them are there in the middle. But anyway, let's keep it for a minute. Okay, gamma of this was 1 plus zeta x, gamma of 1 plus zeta x, and gamma of 1 plus x.
Here you are avoiding, you are approximating the 1 for alpha.
What?
I mean, alpha also has its 1.
Alpha also has its 1, but that, since it's the same between both, you're right. Let me just ignore these alphas. To the extent that this is okay, that will be okay. I should do it a little more carefully. Okay, but now let's look at these. Each of these has its corresponding guys. Okay, so what are we going to get? You see, what we will get approximately is zeta x factorial square. Because we go down to this zeta x. Oh no, or does it cancel? No, it starts cancelling, right? Just a minute.
In denominator only is square.
Yeah, when there's large cancellation. I have to be more careful. Let me use Stirling. Okay, let us do this. I'll leave this as an exercise for you for next class. Check that this thing goes like e to the power minus s into something, and compute this something.
Means x into something.
What? E to the power minus x into something, and compute what that something is. Okay, do it properly. I may have been too sloppy going from here to here, but just do that with that. What? Zeta dependent. This thing will care about the zeta, and therefore will care about theta. Okay. So please check that and somebody show it to me next class. The important thing here is this factor. This is also important. But this factor tells you that in string theory, the amplitude high energy fixed angle amplitude decays exponentially. Okay? Now, this never happens in quantum field theory. Why is that? This is because extreme high energy scattering in quantum field theory is always governed by the UV fixed point. And the UV fixed point is either free, okay, which you approach typically like through asymptotic freedom, so you get a log, or in non-trivial cases is a interacting fixed point, in which case scattering amplitudes grow like powers, because in conformal field theories everything grows like a power. Okay, so this may decay at high energies. In fact it usually does decay, but it does not decay exponentially fast. Okay, this exponential decay here is a sign of something. You know, there's a classic, just 1 minute I'm letting you go. There's a classic physics experiment done around 1900 where this exponential decay was first seen. Can anyone tell me what that was?
Oh, black body radiation.
No, yeah, nuclear. Oh, there's a person's name associated with it. It's called Rutherford scattering. Okay. Yes. What you did was you take an electron, scatter it off an atom. Okay? And you see that most of the time, the scattering decays just exponentially, because the scattering of an electron off a charge cloud, first approximation in the Born, in Born approximation, you've got some charge cloud here. You go in with some momentum k, and you go out with some momentum k prime. And you might remember that the final scattering amplitude is the Fourier transform of the potential with respect to k minus k prime.
If it is power law, then it is exponential in the
Exactly. Now there is this lovely theorem that any analytic function, its Fourier transform decays exponentially at large k. So if k and k prime both become very large, because there is this analytic thing, this always decays exponentially. What's hence the length scale of that exponential? It's the length scale of the cloud. So it's this basic fact that Fourier transforms of things with a certain size have almost no support or much lower than that size. And that statement for any analytic thing is that almost no support is always exponential or faster. Okay? So that fact was something Rutherford saw. Then he also saw violent scattering of the nucleus. That's not important for us. Okay? So there immediately he used that to interpret that fact as saying that look, this nucleus atom is mainly a big fluffy object, then there's also something small. Okay? It's the same thing in string theory. You're seeing a string, you're scattering it off something big and fluffy, namely the string. The string has some size, set by square root alpha prime. Because you're scattering it off something big and fluffy, for the same reason, the whole thing decays, the amplitude decays exponentially. Okay? So the decay the exponential decay of this amplitude is a sign that the things that we are scattering are not point-like.
Yeah, that string theory has listed extended objects.
Yeah, that you're scattering off an extended object. That is what that exponential decay tells you about. It's also at the heart, it also is the heart of the finiteness of string theory. There are no UV divergences in string theory. Intuitively, why? Because scattering amplitudes in UV die off very fast. Okay, next class I'll tell you about Regge behavior. I'm sorry I went over time now.